Welcome. In today's video, we're going to derive the maximum likelihood estimators for the discrete uniform distribution. So to begin with, let us first define the problem. So suppose that x1, x2, all the way to xn, all are independently and identically distributed with a discrete uniform distribution with parameters a and b. Then the PMF, or the probability mass function of each xi, is given by the following. So px of xi given the parameters a and b is by definition equal to 1 over b minus a plus 1. And this is true for xi in an element of a plus 1, all the way to b minus 1, b. Now, alternatively, we can write this in another way, and we could say this is equal to 1 on b minus a plus 1 multiplied by an indicator function, and an indicator function where xi is an element of a plus 1, all the way to b minus 1, b, where, and now we could say x is an element of the real number line. And all this, this indicator function is really saying is indicator function of xi is an element of a plus 1. Well, let me rewrite that a little bit neater. Xi is an element of a plus 1, b minus 1, b. That is simply takes two values, 1 and 0. It takes 1 where the statement inside the indicator function is true. So in other words, xi is an element of a plus 1, b minus 1, b, and 0 in all other cases. So I'll say otherwise. So now we're going to, I've written it in this form, by the way, because this form, or this formulation that I've written here, is going to help us actually derive the maximum likelihood estimate. So first thing that we typically do is we typically derive the likelihood function. So the likelihood function L with n data points for the parameters a and b, given our set of data x, where x tilde is sort of a vector of our data, x1, x2, all the way to xn, it's a vector of data, that by definition is equal to the product of I equals 1 to n of all the respective pxi given a, b. And then this becomes equal to the product of I equals 1 to n, and now we're going to substitute in the formula that we had above. This one here, copy that down, paste that in here. Now our next step is to recognize that a product of, well, the product of I equals 1 to n of two terms multiplied by each other is, we can simply say that's I equals 1 to n of 1 over b minus a plus 1. That's the first product. I'm just going to make it more clear that it's the product of both in the first instance, multiplied by the product of I equals 1 to n of I, xi, an element of a plus 1, b minus 1 to b. So far, so good. So with the first term, what I'm going to note here is that although there is no index actually dependent, or there's no I index within this product here, we still have to multiply this number by itself n times by virtue of the fact that we've got this product at the front from I equals 1 to n. So in short, this just becomes 1 on b minus a plus 1 all to the power of n. For the second term, I'm going to express this I xi in an element of so on and so forth as a little bit more of a something a little bit more compact. One, because it's a bit challenging to keep on writing, but also because it will make our life a bit easier to comprehend in a little bit. So let's have a look here. Instead of saying xi is an element of all these numbers, instead what I'm going to say is we can say that statement is true, one, if a greater than or equal to xi greater than or equal to b. That's statement 1, I suppose you could say. And then statement 2 is x or xi is an element of the positive integers, you could say. So, or sorry, not just positive integers, but negative integers as well. So I'm going to put z is an element of the integers. And one, this is more compact, but it also now kind of gives us this domain, I'll say a range of x values, and it'll help us explain this in a little bit. Now, from here we recognize that we've got b minus a plus 1 still to the power of n. And then for the second, for this product here, I'm just going to write out this product for all of the cases. So it'll be the indicator function that x1 is between a and b, and x1 is an element of the integers, times dot 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 times all the way to I a xn. b xn is an element of the integers, as you can see here. Now, one interesting point about the indicator functions is a unique property that when you multiply indicator functions together, what you're left with is a new indicator function which effectively holds all the statements true. So what I mean by that is, well, all the indicator functions either take a value of 0 or 1. Now, if any of the indicator functions in this series of multiplications is equal to 0, any of them, then the whole multiplication itself collapses to 0. So the only way that you can get 1 out of this product of indicator functions is if each of the statements is true. And so you basically arrive at a new indicator function. And that indicator function will be given as the following. So we've still got the b minus a plus 1 to the power of n out the front. But now we've got an indicator function which says x1 has to be greater than or equal to a and less than or equal to b. x2 has to satisfy that property. x3 has to satisfy that property all the way to xn. Or in other words, we can just write a is less than or equal to x1, x2, dot, 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 xn are all less than or equal to b. So we've satisfied the first statement here. Then, of course, we've got the second statement, which all of them are positive integers. So now we can write x1, dot, 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 xn are elements of z. And that satisfies our second statement. So quite nicely, we've summarized this into one indicator function. And we can actually do one more bit of simplification here. And that is to note that 1 on b minus a plus 1 to the power of n. This statement here that we've just written is actually, we can use what are ordered statistics. And remember, our ordered statistics here, I'm just going to write it on the side, is x1 is equal to the minimum value of x1 to xn, and you've got x subscript n in brackets is the maximum value of x1 to xn. Right? So, in this case, if all of the values of x1 through to xn are between a and b, this effectively means that the lowest statistic, which will say x1, is greater than a. The highest statistic, or I'll say b, and the highest statistic here has to be less than or equal to b. Otherwise, this statement isn't true. So the maximum value has to be greater than b, less than b, and the minimum value has to be greater than a. And then, of course, you still have the condition that x1, x2, xn, an element of z over here. So that's the likelihood function. So I'm just going to pause there, and I'm going to take a screen grab of that, copy and go to a new page. And I'm going to paste that here. And here it is in a bit more tidied up form. Rewrite that as x and an element of z. It's not a squiggly bracket, but a circular bracket. Okay. And again, this is our likelihood function for a, b, given x tilde. Now, typically in these circumstances, what we would do is we would take a derivative of the function, and we'd have to then solve the derivative, set the derivative equal to 0 to solve for the maximum likelihood estimate. In this particular instance, we don't need to do that. We need to actually make an important note here. Well, there's two important notes here. One note is to maximize the log likelihood function, just the likelihood function, AB given x tilde. This is the equivalent of maximizing the first component, 1 on b minus a plus 1 to the power of n, which is, if you want to remember, this will end up being a fraction. In fact, not only will it end up being a fraction, it will end up being a fraction given by, I'm just putting through the power down the front. If you want to maximize this fraction, you need to actually minimize the denominator. So maximizing that is the same as minimizing b minus a plus 1 to the power of n, which is the same as minimizing what's in the brackets, b minus a plus 1, or equivalently, you could just say, because the plus 1 isn't going to change, you can't alter the plus 1, it's the equivalent of just minimizing the difference between b and a. We also have a second point to make here. We've focused on the first component of this. We've now got to focus on the second component of this. And the second component of this is the likelihood function, has to actually be a positive number, in that we want this statement to be true. This has to be equal to 1, otherwise this statement collapses to 0, and then the likelihood function collapses to 0, which is not what we want. So really, the second condition to maximize the likelihood is we need to make sure that x1 beta xn and x1 dot 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 to xn is equal to 1. Or equivalently, this is just actually the same as writing the statement inside. Copy, paste. This is the equivalent of writing the statement inside. So I'll just write implies that. Sorry, apologies, is an element of z. I forgot the element of z in my likelihood function. An element of z. Great. So, we've done that. Now here's the interesting part. We can actually combine these statements together. So 1, b minus a needs to be a minimum. And also, the value of a, if we have a look here, is bounded, has an upper bound, and the value of b has a lower bound. Now, I'm going to add one more statement here in part 1. If you're going to minimize b minus a, this is the same as minimize b, maximize a. Because if we maximize a, then we're subtracting a larger number, and if we minimize b, we're subtracting from a smaller number, giving the smallest difference possible. Now, if we need to minimize b, and we know that b at best has a lower bound of xn, that means we can set our maximum likelihood estimate to actually be equal to the lower bound. And equally, because we know we have to maximize a, but a has an absolute maximum of the lower, or the statistic x underscore brackets 1, then we can set our x, or our a hat, to the minimum value of our data set. And that, ladies and gentlemen, is how we would derive the maximum likelihood estimates for a discrete uniform distribution. Thank you for watching. Hope to see you in the next video.